and then the sensor will be give a feedback. Okay, will be feedback. So is it 20 degrees Celsius or not? If, for example, like, okay, for example, our sensor give a feedback is 19 degrees Celsius. So our system will be increase. Okay, our system will be increase our temperature to the another 1 degree Celsius to 20. Follow the set point. So the sensor is some device to give a feedback. Okay, to give a feedback to our system lah. Okay, this is some example. All right, so this is our example. This is our input. Okay, and then we have this one. Okay, and then this is our we call a controller. Okay, controller, and then this is our system. For example, like our aircon. Okay, we can assume as aircon, and then this is the output. Okay, so we have the feedback. Okay, the feedbacks. Actually, the feedback is the sensor lah. Okay, this is we call the sensor. So the sensor give a feedback to our system, to our system. Right, I mentioned to you, for example, like our aircon. Okay, so this is our air conditioner. So our set point, we set 20 degrees Celsius, and then so this is our sensor. So sensor will be detect is it 12 or not. Okay, that's why here we have a plus minus. Okay, for example, like, so the sensor detect is 90 degrees. Okay, 90 degrees. So that means, so the controller will be increased. Okay, this controller will be increased to another 1 degrees, so that the outputs, okay, the output will be follow the input lah, 20 degrees Celsius. So that is the function of the sensor lah. So the function of the sensor is to give a feedbacks. Okay, to give a feedbacks to our system lah, to our system. Okay, so you can see this one why they put the sensor, why they put the transducer. Okay, some actually the both is the similar. Okay, it's the similar. Actually the sensor, alright, the sensor actually they have only the sensing, we call the sensing element. Okay, and for the transducer they have the sensing elements and they have the transducing transduction. Okay, sorry, transduction elements. Okay, so that is different between the sensor and transducer. But nowadays, most of the sensor that also include the transduction element. All right, so that's why some of the book they refer to transducer, some of the book refer to the sensor. Before this, the sensor only they have only sensing element. All right, so they don't have the transduction elements. Okay, that's why we need some transduction element, okay, to give the output here. All right, so for example, like this sensor just give a sensing element. So how to convert? Actually, the sensor will be give the either in the analogs, okay, analog signal, digital signal, or frequency lah. Okay, so and then we have another, we call the transduction element to convert into the from output of the sensor to the another form lah, another form. For example, to the temperature. So that's we need. That's why we call the transducer. So the transducer is the they have the sensing element and transduction elements. Okay, so that's compared than sensor. But that I mentioned to you, most of the sensor now, because of the digital, so a lot of sensor that also include the transduction element. That's why we can also the sensor or some of the book refer to transducer, but the both will be almost same lah, almost same. Only if we are focus only the sensor, but the sensor only have the sensing element. Okay, if we focus on the transducer will be have a sensing element, and another one is we call the transduction element. Okay, so that is a different lah. That's the difference between the sensor and transducer lah. Okay, the transducer they have another part. Okay, another part sometimes we call the signal conditioning. Okay, signal conditioning lah. So that is the difference between the transducer and sensor. But that mentioned to you, nowadays most of the sensor they also have the transduction element. That's why now we can also call the sensor or call the transducer. Okay, so the objective of this topic is at the end of this chapter, students should be able to first explain the operation and function of the transducer and sensor. All right, so hopefully you know what is the transducer, what is the sensor. All right, so explain the application of the transducer and sensor. Okay, and then explain the limitation of certain transducer and sensor. And last but not least is differentiate several functions of transducer in order to choose the correct type of transducer in instrument application. Alright, so this is our objective for our topic for chapter 7, sensor or transducer. Right, so this is you can see this one. So that is definition of the sensor and transducer. Right, so you can see this one. For the sensor, it is a body which react to the physical, chemicals, or biological condition it sense. It can be considered as the detector. So that means the sensor will be give feedback. Okay, give a feedback to the our system, or sometimes we call the detector. Detects. That means detect any outputs. Okay, any output and then give to the system . And then the transducer, you can see the transducer is a conversion the energy from another form to another is known as the transduction. So transducer serve for this purpose . Okay, that's why I mentioned to you the difference between the sensor and transducer. So the sensor only they have the sense. Okay, they have only the sensing element. They just send the output. Okay, for example, just detect the temperature, but the output of the sensor may be on the analogs. Okay, maybe on the analog, or maybe some type of the electrical forms such as a voltage. Okay, current and so on. Okay, and then we need some transducer. Okay, transduction to convert. Okay, to convert from output. Okay, output of the sensor, for example, like a voltage to for example, to our temperature, to another form to our temperature So that's why we call the transducer. So first, the transducer that you can see this one, the transducer they have the sensor elements, and another one we call the transduction element. Sometimes we call the signal conditioning So first will be sense the output, and then the output will be changed to what the another form we want. For example, so the output of the sensor, in maybe sometime maybe in the voltage. This is analog. For example, this is analog or for example like digital, maybe the output of digital 10 10 0 0 1 For example, this is on the digital. So this is the analog. So normally in the analogs, and then so we have another part we call the transduction, or sometimes we call the signal conditioning, to convert from output of the sensor to the what type of you want to use this sensor. For example, for temperature, Celsius, from voltage to Celsius. That's why we need some we call the transduction element or signal conditioning. That means will be convert from output of the sensor to the output that you want. For example, like temperature or another form of the sensor that you want to measure. Right, so you can see this one. The transducer is more than sensor. It consists of the sensor, actuator, along with the signal conditioning circuit sometimes we call the dimension 3, we call the transduction element So that's why the sensor only have the sensing element. And then another part for the transducer, we have the transduction. Transduction element. All right, so the sensor will be detects the react to the physical, chemicals, biological condition, and then the signal conditioning will be convert. Will be convert from one energy to another energy So one form to another form For example, to voltage to temperature, voltage to speed, for example. Any output So that's why we need some we call the transduction element. But that I mentioned to you, nowadays most of the sensor they also include the both. They also include the sensor and also include the traditional signal conditioning. So that's why some of the two we refer as the sensor, Okay, some of the refer to the transducer, but the both will be nowadays will be similar because of sensor now they also have the signal conditioning. Okay, they just put the signal conditioning. Before this, the sensor only one part, and then the transducer will be combination between the sensor and signal conditioning. But nowadays, the sensor, most of the sensor, for example, like digital sensor, that also include the signal conditioning lah. So automatic will be changed from voltage to what type of the output that you want. Alright, so this is the difference between the sensor and transducer, but the both almost similar. Okay, almost similar. Alright, so next, the transducer defined as the device that receives energy from one system and transmit to another. Okay, often in the different form such as electricals, okay, mechanical, and acoustics. Okay, so basically there is two type of the transducer. So we have the electrical and mechanical. So because of this subject belongs to electrical, right? So most of the sensor will be covered on the electrical part lah. Okay, electrical part. For next, for the next, most of the sensor we just cover for the electrical part. Okay, so next we have the mechanical part. So for example, like mechanical part, we have the torque. Okay, we have the torque sensor. We have the flow sensor. These some example, some example of the mechanical sensor lah. We have the pressure sensor. Okay, we have the pressure sensor, and then we have the force sensor, and so on. Okay, so this is some mechanical part lah. So, but that I mentioned to you, our syllabus focus more on electrical lah, more on electrical transducer, more on electrical sensor. Alright. So the electrical output of the transducer depends on the basic principle involved in the design lah. So the output may be analog, as I mentioned to you, maybe analog maybe in terms of the voltage. Okay, maybe in terms of the current. Okay, so and then our digitals, okay, the output may be in the digital, but not that mentioned to you, nowadays most of our sensor you use the digital lah. Okay, because of the chips, okay, easy to design and easy, a lot of input output that we have to measure, okay, for the sensor. And then we have another one is the frequency modulated lah. Okay, modulated is the FM, frequency modulation lah. Right. So this is some output, okay, for the electrical transducer. Most of the sensor nowadays they use the digital output. Okay, digital something like this lah. So we have 11001. Okay, this is some example lah. Example maybe like this. Okay, maybe 110. Okay, 100. Okay, 111. This is we call the digital lah. And then, for example, right, from analog to we have another converter lah. For example, our sensor is analog. Okay, our sensor is the analog. Okay, our sensor is analog. So our output is the digital. So we have another one device that we call the converter to convert from analog to digital lah. Okay, so we have this one analog to digital. Okay, so we call it ADC. Okay, ADC, analog to digital converter. Okay, converter. And then from digital to analog, so we have the DAC. Okay, DAC, digital to analog converter. Okay, for example, if your sensor in the analog, so we have another device, okay, that we call the ADC. Okay, to give to our system lah. For example, our system using the digital, so that's why we need some converter to convert our output. Okay, that's why we have a analog to digital converter, or sometimes we have the digital to analog converter. So this some of the device that convert from analog to digital or digital to analogs. Okay, so next, an electrical transducer is the device that convert a physical, mechanicals, or optical quantity into the proportional voltage and current that mentioned to you. So the output, for example, like analog, either in the voltage or current lah. Okay, or current. That is for the electrical. Okay, for electrical, for example, like normally the quantity for electrical for analog is the voltage or current lah. Okay, So also we have the power, but power actually is a combination between the voltage and current. That's why the basic is the voltage or current, right? And then an electrical transducer must have the following parameter lah. So they have the 5 parameter that you have to follow. Okay, the first parameter is the linearity. Okay, linearity. That means for example, this is our output. Okay, so this is our input, for example. So maybe relation will be linearity lah. So this is our output for our system. So linear relationship between the physical parameter and the resulting electrical signals. Okay, and then second parameter is the sensitivity lah. Okay, sensitivity defined as the electrical output per unit change in the physical parameter. Okay, for example, okay, that I mentioned to you like our aircon. Okay, so for example, this is our system. This is controller. This is our aircon, for example. Right. So okay, so we have here. We have this is our feedback lah. Okay, sensor. We call the sensor. Right, so maybe we set 20 degrees. Okay, so actually the output here maybe in the voltage. Okay, maybe in the voltage. All right, so that's why we need some we call the transduction element to convert from voltage to temperature. Okay, temperature. That's why every voltage so we represent what the range of the temperature. That's why some example of this one volt per temperature. All right. Okay, and then the higher sensitivity is desirable lah. Okay, so we need our higher sensitivity lah for our system for our sensor lah. Okay, and then next third is the dynamic range. Okay, transducer must have the wide range, wide operating range. All right. So that's why if you want to design you want to use the sensor, make sure you have to know the operating range lah. That's another important parameter that you have to know. For example, okay, this sensor detect from 0 to 100 Celsius. Okay, if you more than 100, okay, more than 100, you cannot use this sensor. That's why we have to know the operating range lah for every sensor or every transducer. Every transducer that we use, we have to know the operating range. Okay, for example, like our sensor just function only from 0 degrees Celsius to 100. So if our system more than 100 Celsius, we cannot use this sensor. Okay, we cannot use because of the operating range only for 100 Celsius. Okay, 100 degrees Celsius. And then next is the repeatability. Okay, so repeatability is the input-output relationship for the transducer should be predictable over a long period of the time. Okay, for example, like if you are test, okay, our sensor, for example, like piezoelectric. Okay, so if you test more than 100,000, okay, 1,000 or 2,000 time testing, so the input-output will be same. Okay, for example, like this one, the input-output. Okay, so maybe linearity. So this is first time, okay, test. Second time almost similar to number 2 until 100 or 1,000. So the input will be same. Okay, that's why we need repeatability lah. Okay, so over a long period of time lah. And then last for the parameter for the electrical transducer is the physical size. Okay, so the transducer must have the minimal weight and volume to minimize the disturbance to the existing condition and current. That's why, so if you can see the electrical transducer, mostly the sensor is very small. Okay, very small because of we want to reduce the minimal weight and to minimize the disturbance. Okay, disturbance to affect our system lah. That's why if you see the electrical, I will show some example lah. Some example before this. Okay, the sensor for electrical is just very small. Okay, very small sensor lah. That's why another parameter, the parameter that we have to know is the physical size. Okay, so the size of the sensor will be minimal because to minimize the disturbance to existing condition and environment. Alright, so you can see this one. So the electrical transducer can be classified into two major categories. First is the active and second is the passive. Okay, what is the active? What is the passive? So you just remember this one. Active not require the external power to operate. So automatically will be operate. No need power supply. Okay, this some example here. Example of the active is the piezoelectric. This one is the piezo. This one is the piezoelectrics. Okay, no need power supply. No need power supply. So this piezoelectric automatically will be function, even they don't have the power. Okay. All right. So compare then passive. Passive will required internal power to operate. Okay, this is some example of the passive transducer. All right, so we call the strain gauge. So they need a power supply lah. Okay, they need a power supply to operate this sensor. Okay, that's the difference between the sensor lah. So one of the sensor will be active, another one will be passive. Okay, the active no required power supply. For example, like piezoelectric or photocell. Okay, this is photocell. All right, this is some example of photocell. Okay, very small. You can see very small. This one, okay, photocell, and also this one we call the piezoelectric, also very small. Okay, this also the the photocell lah, but in the housing, in housing. For example, this one will be detect the light. Okay, for example, like we can set our room. Okay, use this one. For example, if the condition is the dark, so automatically will be on the lamp lah. So this is a sensor that detect the condition of the room, for example. All right, that's we call the photocells. Okay, so that is a category lah, the category of the electrical transducer. They have active transducer. They mean active, no required power supply to operate the sensor. And then for the passive, require the external power to operate lah. Okay, for example, like if you use the passive, okay, that's why you have to know. Okay, that's why you have to know either this sensor is the passive or active. So if the passive, we have to use the power supply. We give the power supply, then we can test. Okay, we can test our sensor. If we don't give the power supply, so this sensor will not operate lah. Do not operate because this sensor will be need external power to operate lah. To on this sensor, to on this sensor, we need extra power lah. Compare then active. So active, we just connect to our circuit. So automatically this sensor will be function. Okay, will be function. That's why this we call the active lah. Active not required the power to operate this sensor. For the passive will be required the power lah to operate the sensor. That we call the major category lah for the electrical sensor. Okay, that's that I mentioned to you. So for the sensor, or sometimes we call the transducer. So they have two element. Okay, two part of element lah. First, they have the sensing element. Okay, so this sensing element respond to change in the physical phenomenon, and then the transduction transform the output of sensing element to electrical output. Okay, so that's why our sensor, all right, so only have the sensing element. The transducer, they have on sensor and transduction element. But I mentioned to you now, most of the sensor they have the both. Okay, that's why we can also call the transducer or also call as the sensor. Okay, but before this, the sensor only they have the only sensing element. Okay, for the transducer, they have the sensing element and transduction element lah. Okay, so this is a electrical transducer, the different electrical phenomena employed in the transduction element of the transducer follow as this one. So this is more on electrical sensor that I mentioned to you. So we for such as a resistive, okay, based on the resistor. Okay, we have the inductive based on the inductor. Okay, we have the capacitor based on the capacitive based on the capacitor, and so on. We have the electromagnetics. Okay, we have the piezoelectric, photoemissive, and so on. Okay, so this is some different electrical phenomena lah will be employed in our transducer. Okay, for electrical transducer, this is we call most of the electrical transducer lah. Okay, that mentioned to you. So our class will be focused on this electrical transducer lah. Okay, we focus on the resistive, inductive, capacitive, and so on. Okay. Alright, so next we go for the resistive position transducer. Okay, on the electrical transducer. So operate under the principle of the resistance change by the physical movement under measurement. Right, so one type of the resistive position transducer as shown in figure 7.1, I will show after this. Alright, so the basic operation of this transducer use resistive, that means use the resistor element, alright, so with a sliding contact or wiper links to the object being measured. Alright, so the shaft and wiper can be moved to the left or right, cause a change in the circuit resistance in figure 7.1. So the output voltage of the circuit given by, okay, so this is actually we use the voltage divider rule. So this one we call the voltage divider rule. So voltage divider rule will be like this. V out, okay, V2 R2 R1 plus R2 multiplied by VT. Okay, so this we call the voltage divider rules. Divider rules. Okay, so this is one formula. Formula for using the resistive position transducer. They use the voltage divider rule. So this one to calculate the V out. So we can use this formula. Okay, V R2 divided by R1 plus R2 multiplied by VT. Right, so the output voltage is proportional to the R2. That means this, okay, this V out, okay, voltage output is depends on this one, the R2, okay, the R2 and this one. Okay, so the resistance of the transducer is distributed uniformly along the length of the wiper movement. So the resistance will be linear. Okay, so this is a circuit. So this is the mechanical. Okay, you can see this one is the mechanical circuit. Okay, and then from this mechanical they convert into the electrical. Okay, similar like this. So this is power supply from A to B. You can see this one. A to B is our supply here. Okay, and then this is our resistor. This is our resistor. We call a variable resistor here. Okay, that means here from R1 R2. So that means R total will be R1 plus R2. Okay, R1 plus R2 lah. So this one will be move lah. Move to the left to move to the right. So you can see this one on the, maybe you can move here or maybe you can move here. Okay, so the total R here will be R1 plus R2 lah. R1 plus R2. Okay, so that's convert from okay, from this one from the mechanical, okay, mechanical structure to the electrical structure, electrical circuit. All right, so we go for the example. So example, all right, so the resistive position transducer is the shaft stroke of the 3-inch, okay, is applied to the circuit 7.1. Okay, the total resistance of the potential meter is the 5k ohms. Okay, the applied voltage VT is the 5 volts. When the wiper is 0.9 inch from the B, what the value of the output voltage? Right, so as we know here, so the total length for R is the R length, we call it length for R is the 3-inch. Okay, and then our R total is the R total is the 5 kilo. 5 kilo, that means R1 plus R2. Okay, R1 plus R2 will be 5k. Right, but when the wiper is 0.9, okay, the wiper 0.9 from the B, so that from the total length is the 3-inch. That means that's why we can get here. We have to calculate what is the R2 first. So the R total will be 5k. So we want to find the, okay, for example like this one. So this is okay, this is R. This is we call the something like R. This is R total, and then maybe the length of this one will be 3 inch. Okay, 3 inch, and then from to B, from this one, maybe this one 0.9. 0.9. That's why we want to find the resistor. Okay, we want to this one we call R1, this one R2. So we want to find the resistor for R2. You can use this formula lah. That means 0.9 inch here divided by 3 inch. Okay, the total length multiplied by 5k. Okay, 5k is the total resistor lah for RT. So equals to 1,500 ohms. Okay, that's the R2. and then we want to calculate the output voltage, we can use this formula. Okay, V naught, okay, R2 R1 plus R2 multiplied by VT. Okay, just substitute the value for R2 and VT, and then you can get the voltage output lah. So the voltage output will be 1.5 volts. Okay, 1.5 volts. So this some example from this circuit. Okay, you can see this one. So the total length here. Okay, the total length here 3 inch. Okay, 3 inch, and then this one, okay, maybe 0.9 inch. Okay, that's why this is we call the R1 and R2 here. So we want to find the what is the R2. Okay, the R2, because of this length is the 0.9, that's why 0.9 over 3 inch multiplied by total resistance. Total resistance is 5K. So that's why we can get the R2. So if you want to find the R1, so just R total minus with R2, you can get the R1 lah. That's the R1. Okay, if you increase, if you increase this position, so the resistor will be increased. Okay, for example, maybe I increase it to 1.5. Okay, 1.5. Oh, okay, this is almost half. Half. So maybe I increase to 2 lah. Okay, maybe in 2 inch. It means 2 divided by 3 multiplied by 5K. Alright, so you can use your calculator. By 3 multiplied by 5K. Okay, so maybe 3000. Okay, so the R2 will be 3.3 3.3K lah, for example, 3.3K kilo ohm, for example. Okay, the R2. Alright, so when we increase this length lah, so we increase. So for example, if reduce the length, so the resistor will be reduced. Okay, it will be reduced lah. Okay, so next another example. Okay, so this one we have another example. So the resistive transducer with the resistance of 5 kilo ohms. Okay, total resistance is 5 kilo ohm. Is used in the arrangement in figure 7.2. Okay, potentiometer R3 minus R4 is also 5 kilo ohms, and VT is the 5 volts. Alright, so the initial position to be used as the reference point is such that R1 equal to R2. Okay, so that means R1 equal to R2 will be same lah. Alright, so if the total resistance 5K, that means R1 R2 will be same. Okay, that means 2.5 lah, 2.5. Right, so for example, the shaft is at the center. That means it's the center lah of this resistor. So at the beginning, alright, so R3 and R4 is adjusted so that the bridge is balanced. Okay, the balance, that means this voltage is equal to 0. Okay, assume that object being moderated move of the maximum resistance of 0.5. Okay, so this one will be moved to 0.5 lah, 0.5 inch to A. Alright, so what is the new value of the VE? Okay, this one new value. Okay, so the total shaft, okay, the total length of the shaft is 5 inch. Okay, so the first you have to calculate the resistor R2 lah. Okay, right, calculate the resistor R2 similar like before this. So okay, 3, okay, divide by 5 and then multiply by, because of first this is initial so right, because of the okay, wait. Okay, 3. Okay, okay, so if the wiper move 0.5 towards the A in this at the center, will be move 3. Okay, move 3 in the from the B lah. So that's why we can get this one. So 3 divided by 5 multiplied by 5K equals to 3 kilo ohms. Okay, 3 kilo ohms. This is formula. This is standard formula to calculate the VE. Alright, so if you refer to the Wheatstone bridge, okay, that is the same formula for Wheatstone bridge. Alright, so that's why R2 divided by R1 plus R2 multiplied by VT minus R4 divided by R3 plus R4 multiplied by VT lah. And then just substitute the value, alright? So the value for R2 and R4 and R3. So you can get this one lah. So the new output is the 0.5 volts. Okay. So this one actually you can refer this one. It actually is a similar like this one similar like DC bridge. Okay. Right, so that is how to get the voltage here lah. Okay, the voltage here. So this one. So that is a standard formula. So V2 minus VR. So to get the V2, this is a formula. We call the voltage divider rule for this one, and then this is a voltage divider rule to calculate the V4. This one. Okay, to calculate the voltage here and the voltage here. Okay, so that's why you can get this. The new VE. So the VE will be appear 0.5 volts. Okay, that is some example lah. Okay, next we go for the strain gauge. Okay, strain gauge is the example of the passive. Okay, I already give the example the picture for strain gauge. Okay, the passive no need the power supply to sense the strain produced by the force on the wire lah. So strain can be measured more easily. So this one need power supply. The passive need power supply. Sorry. Okay. So the passive need a power supply lah to on the sensor. Okay. The strain can be measured more easily by using the variable resistance transducer. It is common practice to measure the strain instead of stress. Okay, of stress. Okay, to serve as the index of pressure lah. As the metal conductor is stretched or compressed, its resistance change since the both of the length and diameter of the conductor change. Okay, so also there is a change in the value of the resistivity of the conductor when subjected to the strains. It's called the piezo-resistive effect. Therefore, the resistance strain gauge are also known as the piezo-resistive gauge. Okay, so so this some example. Okay, some example of the strain gauge. Okay, so maybe you can see on before this the application of the Wheatstone bridge. They put the strain gauge. Okay, so they have the single strain gauge. They have the quarters. They have the full bridge. Okay, full of the strain gauge. Okay, so this some example lah. Some example of the sensor. Okay, this sensor need power. Need power to operate this sensor. Okay, so this is some example. Okay, you can see this one. Alright, so this is strain gauge. So the technique, this one, some of they use the semiconductor, they use the foil, or they use the metals. Okay, the metal. Right, so this one. So to on this one, okay, this sensor, they need the power supply lah. They need the power supply to active this sensor. Okay, so this one. This is a drawing, and then actually this is actual lah. Okay, actual sensor, our sensor lah. So this sensor need power because this is passive. Okay, passive transducer, so they need a power supply to on this sensor. Okay, so this some example for strain gauge application. Right, to detect maybe you can detect the pressure. Okay, so maybe you can detect the weight. Okay, the application of the strain gauge, maybe you can measure the weight of the human. Okay, and some you can use. Okay, we can use as the measure the pressure or measure the weights. Okay, and so on. That is some application of the strain gauge lah. So we can measure the weight or we can measure the pressure. Depends on the application for the strain gauge. Alright, so when the gauge is subjected to the positive stress, okay, so its length will be increased while the cross-sectional area decrease lah. So since the resistance of the conductor is directly proportional to its length and inversely proportional to its area of the cross-section, so the resistance of the gauge increased with the positive strain. Where is the value for this one? So this is actually this is formula to calculate the resistance. Maybe you can remember I think the previous class to calculate the resistor. Normally the resistor you can measure using the multimeter. Okay, but this is formula. This formula to calculate the resistor actually. Okay, right. So the formula is to calculate the resistivity is the resistivity rho multiplied by length divided by cross sectional lah. So that is his formula for calculate the resistor. Okay, and then three main type of the strain gauge they mentioned to you. So they also have the wire strain. They use the wire. So for example, this is our strain gauge. Okay, this one is maybe they use the, okay, for example like this okay, connect here, maybe connect here. So maybe they use the wire. Okay, maybe you can use the wire, or maybe you can use the foil. Okay, and another one they use the semiconductor strain gauge. Okay, they have three types. Okay, for strain gauge, so using the wire, okay, using the foil, or using the semiconductor lah. So, okay, so we go one by one. For the using the wire, okay, wire. All right, show figure 7.4, show the metallic bond strain gauge. Okay, I will check. All right, so example this one so this you can use the wire. This one is a wire fine wire. Okay, fine wire here, and then this is positive lah, positive and negative to on this sensor. Okay. All right, so the fine wire element is cemented to the thin sheet of the paper or Teflon or bakelite. Okay, so the measurement of the sensitivity of the material to strain is the called gauge factor lah. So the formula for gauge factor is given by this one So actually gauge factor equal to K equals to delta R divided by R, okay, over delta L divided by L. Okay, what is the R? What is the, okay, we can check what is the R. Okay, R is the initial resistance, okay, without strain. Okay, delta R, okay, delta R is the change in the initial resistance, okay, in ohms. And then we have delta L, okay, this one that we call the delta L is the change in the length in meter. Okay, this one in the ohms. Okay, this one in the meter lah. Okay, in meter And then for L is the initial length initial length in meter without strain lah. Okay, so this is formula formula for calculate the gauge factor. Okay, so this is some example. They use the metallic bond strain gauge. Okay. Alright, so this is some example. Alright, so you can straightforward lah. Okay, you can straightforward using this formula K equals to delta R divided by R. Okay, delta I divided by delta L divided by L. Alright, so from this one, okay, given gauge factor will be given K. This one gauge factor. Okay, K equal to 2, and then R equal to 125. Okay, so we want to calculate this one So calculate this one So and then the length, okay, the strength, okay, the strength is the right. So automatically from this formula you can get 2 multiplied by 2 multiplied by 1 multiplied 60. So you can see on the slide. So automatically the delta R, okay, delta R is the change in the initial resistance. Okay, is the 240 micro ohms. Okay. Alright, so this is the answer lah. Okay, so we proceed next one. Okay, the next one, this is some example So you can see the Wheatstone bridge before this. I will show you before this. Okay, they use the quarter. That means the only two. Okay, there's maybe we can use one. One we call a single bridge. Okay, single bridge, and then they use the two. Two is a quarter. Maybe have the full bridge. That means we have 4 strain gauge lah. Alright. Some example where the strain gauge is used. So they have the stress. Okay, this is unstressed Normally the unstressed is dummy It's the dummy strain to balance the bridge lah, because of we want to balance this bridge, so that's why we have another one strain gauge. So one for the stress, another one for unstressed lah. So unstressed is the dummy lah, dummy strain to balance the bridge. Okay, next we have the foil strain. So this one similar like wire, so but they use the foil lah. They use the foil here. The concept will be same. This is our supply. Okay, to on this one, and then this type is the foil. Okay, so another one they use the semiconductor lah, but this one using the foil lah. Okay, so this look like the wire gauge, except they use the metal foil lah. Metal foil as the sensing element. This one. Before this they use the wire, fine wire, very small wire, and then this one you use the metal foil. Okay, so okay, the foil strain gauge is shown in 7.5 lah. So this one, some example. So the foil strain gauge has the same characteristic as the wire strain gauge. Okay, will be similar. Okay, will be similar lah with the wire strain gauge. Okay, next is the semiconductor strain gauge. Okay, semiconductor strain gauge has the very high gauge factor. Okay, height has 50 times of the wire strain gauge. Okay, right? Figure 7.7 show the construction of the semiconductor strain gauge, and then the resistive material used to make this gauge is the semiconductor type such as germanium and silicons. Okay, even though semiconductor have very high gauge factor, it is very sensitive to change in the temperature. So and its linearity is poor, and it is very more expensive lah. That's why normally for the strain gauge they use the metals or wire lah, metal foil or wire. Okay, because of semiconductor very expensive, very expensive, and the linearity is poor for the semiconductor. Okay, so this is some example of the semiconductor strain gauge. Okay, this one they use the semiconductor, but the concept will be same. This one is for the positive, and then they use the gold lead. Okay, and then they have the semiconductor. Okay, the advantages of the semiconductor is the smaller size, okay, higher sensitivity and higher gauge factor, low hysteresis. Okay, that means more elastic lah, and then longer lifetime. Okay, that's the advantages of the using the semiconductor, semiconductor gauge. Okay, and then but disadvantage of the semiconductor is the very sensitive to the temperature, expensive, okay, non-linear, resistant to the strain relationship. Okay, varying from 10 to 20% from the straight line of the equation. Okay, that means so this is not dimension 2 is not linear. It's not linear. This one is the non-linear lah, non-linear resistant. That means you can see the varying is 10% to 20% from the straight line. For example, this is our output. So maybe varying from something like this. Okay, 20%, 10% to 20%. Okay, from the straight line. Okay, so but you can see this one. So this limitation can be overcome through the software compensation. So we can use the software. Okay, maybe you can use the another, for example, like we can use the MATLAB software to reduce this. For example, this one, the limitation, this limitation to semiconductor. Alright, so next we go for the capacitive transducer. Okay, capacitive transducer operate by linear change in the capacitance. Okay, that means from the capacitor lah. Okay, from the capacitor. So the capacitance of the parallel plate capacitor is given by, okay, this is formula. Actually, this formula for calculate the capacitor. Okay, in farads. Okay, so this is formula. I think maybe you study this one on the physics. Okay, the basic physics. So how to calculate the capacitor, how to calculate the inductor, how to calculate the resistor. So that actually this is how the capacitor comes. Okay, K is the dielectric constant multiplied by area of the plates. Okay, and then multiplied by epsilon naught. Okay, this is a permittivity. Alright, and then this is a fits. Given is a fits, and then divide by plate. Okay, the plate placing in the meter. So this is a formula for calculate the capacitance. Okay, so this some example you can see. All right, so on the slide here, so this is an example of the transducer for capacitance transducer lah. Okay, so you can see from the equation. I will show after the equation 7.3. This one, equation 7.3 here. So the capacitance increase if first is the effective area of the plate is increased, and second is the material of the electric constant lah. So this one, area and the electric constant. So this one, this one will be increased because this one will be fixed. Okay, and then this spacing lah. Okay, and then the variable plates area transducer is shown in the figure 7.8. Okay, so it's after this, I will show after this. It's made from the fixed plate called a stator and the movable plate called a rotor lah. So that's why we have two plates lah. So one will be fixed, we call a stator. Another one will be movable plate, we call the rotor lah. So rotor will be moved, okay, will be moved either to the clockwise or anti-clockwise. So the capacitance of the transducer is changing as the rotor change its position relative to the stator. Okay, this transducer can be used to detect the amount of roll in the aircraft. Okay, this one, the function of the capacitive is to detect amount of roll. Okay, amount of roll in the aircraft. Okay, the function of the capacitive transducer. Okay, this one, you can see this one. Okay, so this is fixed. Okay, this stator will be fixed, and then this is will be move. Okay, either move to the move to here or to move here. All right. So that's why you can see the weight will be changed lah. So initially will be here, and then will be changed to here or change to here lah. All right. This one is the we call the capacitive transducer. Alright, so another example of the capacitive transducer is the capacitive pressure transducer, as shown in the figure 7.9. Okay, this sensor is designed to measure the pressure lah. Okay, measure the pressure in vacuum. So metallic diaphragm, okay, will be moved to the left when the pressure is applied to the chamber, and to the right when the vacuum is applied. Okay, the diagram is used as the one plate of the variable capacitor lah. So the capacitor transducer is simple to construct, inexpensive and effective for high frequency variation. Okay, so this is advantages of the capacitive lah. Simple to construct, okay, cheaper, and the one is the effective to high frequency variation. Okay, so this, for example, is to detect the change in the high frequency acoustic signal. Okay, so this is some example example of the capacitive pressure transducer. Okay, you can see this is this reflection diaphragm. Okay, so this come our pressure here. So and then will be this is our dielectric lah. Okay, so if this one will be moved, so our pressure will be increased. Okay, that's why they are how their works lah. So for example, this diagram like this. So now is the normal lah. But if we have pressure, so depends on the pressure. If our deflected diaphragm will be here, so our pressure will be increased. Okay, next we go for the inductive. Okay, inductive based on the inductor lah. Okay, based on inductor. Okay, the inductive transducer may be either of the self-generating or the passive types. Okay, the self-generating types utilize the basic electrical generator principle. For example, like motion between the conductor and magnetic field induce a voltage in the conductor. And then, for example, for inductive conductor, they use for tachometer. Tachometer is to measure the speed lah, to measure the speed or measure the velocity lah. Okay, the example of the self-generating transducer, which directly convert speed or velocity to the electrical signal. Okay, the passive type inductive transducer utilize the change in inductance. Okay, depends on inductance lah. Okay, for inductive. So the inductive electromechanical transducer convert physical motion to the change in the inductance. Okay, so this is a formula to calculate the inductance. Okay, so mu r multiplied by mu naught multiplied by n. N is number of turns. Okay, power of 2, and then multiplied by area and divide by length. All right, so this is formula. This is formula for calculate the inductor. Okay, so this is you can see this one. This is a linear inductive transducer, and then this is angular. Angular. Alright, so this some example lah. You can see this one. So how from these two types so convert to this one lah. Okay, inside this one, whether they use linear inductive, this one maybe linear inductive. Okay, so maybe another one we have the angular like this. Okay, that means when we change this one, okay, when we change similar like resistive. Okay, before this we use the resistor. Now we use the inductor lah. We can use inductor. So when this output will be changed, the value of the inductive will be changed lah. Follow the output. This one. Okay. So this one, another one, we have the inductive transducer variation of permeability. All right. So you can see this one. For example, here, this is output, and then we have the coil, and then we have this one is the ferromagnetic former. And then iron core lah. Right. Okay, so figure 7.5 show the variable reluctant transducer. Okay, the transducer consists of the coil wands on the ferromagnetic core. The displacement which is to be measured is applied to the ferromagnetic target, and then the core and the target are separated by the air gaps, and then the self-inductance of the coil is the inversely proportional to the length of the gap lah. So when the target is near to the core, so the length is small. Thus the increase of the self-inductance. Okay, this one. So this is a variable reluctant transducer. Okay, so this is our output, and then we have the core. Core normally we have the ferromagnetic. Okay, ferromagnetic, and then this is our target, and then we have the air gap here. Okay, this is formula. Formula to calculate the inductive. Inductive. So this you can use this formula lah. Alright. So n power of 2. N is the number of turn. Okay, divide by reluctance of the iron part and plus reluctance of the air gaps. Normally, iron reluctance of the target, okay, or iron will be negligible lah. Negligible. So will be cancel out lah. Okay, will be cancel out. So because of negligible, and then the calculate the inductance will be n power of 2 divided by Rg, reluctance of the air gaps. Okay, to calculate the air gap, we use this formula lah. Okay, length of the air gap divided by permeability multiplied by area of the flux through the air. Alright, so this is formula to calculate the inductance lah. So we can substitute this Rg to this equation, and then you can get the inductance lah. So the Rg is proportional to the Lg, right? Thus the L is inversely proportional to the Lg. Lg is the length of the air gap lah. Okay, alright. So the last for today for our sensor will be LVDT. LVDT is the linear variable differential transformer. Actually, it's the transformer. It's a transformer. Actually, you have to know what is the transformer. This transformer convert from another for example, from low voltage to high voltage, or low to high voltage to low voltage. That is the we call the transformer lah, to convert from another input to another to output to the another outputs. Okay, so the LVDT is the passive inductive transformer. This means we need power supply to active this sensor. Okay, so the basic construction is shown in the figure 713A, while the figure 713B is show the electrical circuit of the LVDT. So the movable soft iron slide within the hollow part of the transformer does affect the magnetic coupling between the primary and secondary winding. Okay, and then the frequency of the AC voltage applied to the primary winding range from 50 Hz to 20 kilohertz. Okay, so this is you can see this one. So actually this is basic construction. This is basic construction of the LVDT. Okay, and then from this one we convert into the electrical to electrical circuit. So you can see this one. So this is our core here. Okay, this is we call a primary. Okay, primary, and then this is core, and then this is sorry, this is secondary. Sorry, this is secondary. This is primary, and then this is from our input. Our AC input. Okay, from this part, okay, you can see from this basic construction of the LVDT to electrical circuit lah. They convert from this part, okay, basic construction to electrical conduction lah. Okay, so this is some formula you have to know to calculate the output voltage of the LVDT is the E0, okay, equals to S1 minus S2 lah. So you can see this one, S1, this one, S1 minus S2 to get the V out. Okay, E0 lah. Right, so they have three possible position of the iron core. So we have first is the normal position. Normal position, that means our output voltage is a 0. Okay, so if we put to the left, right, so that means S1 greater than S2. So that means our output voltage will be S1 minus S2 lah. Okay, so if we go for the right position, so that means our S2 greater than S1, thus our output voltage will be S2 minus S1. Okay, that is a formula that you have to remember lah, this one. Actually, this is basic formula. Okay, but you have to know lah. So we have three possible position. So if normal, that means it will be 0. Okay, if to the left, okay, to the left, that means S1. This one more to the left lah. Okay, more to the left. Okay, kalau for example for the right position, that means E0, okay, equals to S2 minus S1. Okay, so this one for the left, for to the right S2 minus S1. Okay, so this one to the right lah, to the right position. Okay, so this is some example. You can see. So this is normal. Okay, is the normal position. Okay, so for example, this is to the left, to the right lah. For example, to the right, okay, and then to the left. Okay, the equation you can see this one. So to the right, S2 minus S1. This one S1 minus S2 lah. Okay. Okay, so this is some variation of the output voltage and displacement, right? So you can see this one, output voltage and displacement. So this one is the in phase and this one is the out of phase lah. Alright, so the amount of voltage change at the secondary winding is proportional to the amount of movement of the core lah. So indication of the amount is the linear motion. By noting which output is increased or decreased, the direction of the motion can be determined. Okay, advantage of this LVDT is the produce higher output voltage for the small change. Okay, for example, like 50 millimeter volt per mm or 100 millivolt per mm. That means every 1 mm will be changed 3 millivolt. Okay, for example, we have 1 milliohm. That means the change will be 300 millivolts. Okay, or 50 millivolt, for example. And then variable range is the plus minus 0.05 inch to plus minus 25 inch. Okay, the sensitivity enough to measure displacement of well below than 0.001 inch. Okay. Right, so I think that's all for today. Okay, I just stop here. So maybe next week we focus on the piezoelectric transducer. Right, so actually I mentioned to you, because of this belong to FKE, belong to electrical, most of the sensor will be covered for the electrical transducer lah. Okay, so Actually, dimension 2, we have another type is the mechanical. We have the mechanical transducer, but on the mechanical we don't cover lah. We just focus on the electrical transducer. Okay, so and then on the teams, I will give one quiz. Okay, you can do after this. You can do your quiz. Okay, simple quiz. And then you can submit next week. I give you 2 weeks. Sorry, another 2 weeks. So you can try. I've already set up in the teams, and then after this you can get the notification from the teams, and then you can try. Okay, so the quiz based on the AC and DC bridge. Okay, AC and DC bridge lah. Alright, so yeah, that's all for today. Alright, so see you next week. And don't forget, try your quiz. And then also submit through the teams lah. So the due date for this one, for the quiz, I think 9 January, 8 January. So we have another okay, another 1 week lah, until Friday next week. Okay, until Friday next week lah. So you can try. So we have only 2 questions. One question to the DC bridge, and another one is the for AC bridge lah. Because of before this we just focus on the tutorial. So tutorial for AC and DC. So now you can try. You can try. This is we call the take home quiz lah. Take home quiz. So you can try lah. You can discuss this one, and then submit to me before Friday. Friday 8. Okay, you can submit through your teams. Right, so if no question, I will stop here. So we will continue next week. So next week we will be finished on our syllabus lah. So we just have the electro. Okay, we have the piezoelectric transducer. We have the temperature transducer. We have the thermal energy, temperature, RDT. Okay, thermistor, thermocouples. Alright, thermocouple, photodiodes, okay, phototransistor, and okay, that's all. So this one will be covered next week lah. Okay, so our syllabus for the sensor until phototransistor. Okay. Right, so if no question, I will stop here. Right, thank you very much. Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, thank you guys.
Thank you, sir. Thank you, sir.
Okay, welcome.